All right, it's great to be here on the last day with you all. Thank you for finding us in the back corner of the building on the 3rd floor. I'm really excited to be here though, talking to you today about building data-rich applications for AI and enterprises on Google Kubernetes engine. My name is Jason Messer. I'm a senior engineering manager for the Google Kubernetes engine storage portfolio of products and solutions, as well as I work on Ray for ML orchestration and reinforcement learning as well. But we'll be focused on the data side of things today and the storage investments and innovations our team has been producing this past year to further accelerate your workloads with performant data planes. Last year, we spoke about some of the innovative solutions we were developing, like Data Cache, Managed Lustre, and Run AI Model Streamer. And today, we will show you how we've brought those solutions to production for some of our biggest customers. You know, the biggest challenge for AI applications today is accelerator capacity, finding it and fully utilizing it. Expensive accelerators require high throughput, low latency data planes to maintain saturation. Today, we will explore how GKE designs for stateful scaling to achieve optimal performance for AI and enterprise databases, such as with ClickHouse and Character.AI. You will learn how to architect storage solutions with Managed Lustre and Cloud Storage Fuse with GCS Rapid to drive peak throughput for training and inference workloads. We'll also demonstrate how storage profiles and attribute classes simplify performance tuning for your workloads. Joining me today is Mustafa Yildirim from Character.AI and Vinay Suryadevara from ClickHouse to share how they are using their data solutions to run their business-critical workloads on GKE. Here are the key takeaways I really want to leave you with if you remember nothing else from the talk today. GKE, with our storage partners at Google Cloud, have built a high-performing, scalable, and reliable data plane, making GKE the best place to run your stateful, enterprise, and AI application workloads. We have engineered a set of container storage interface drivers and Kubernetes controllers that optimize and connect all of the available Google Cloud storage offerings, including GCS, Hyperdisk, local SSD, Lustre, file store, and others to your pods for stateful workload applications. We've solved the problem of scaling our control plane to offer all of these storage solutions to you transparently via persistent and ephemeral volumes. Secondly, we've seen tremendous growth across all of our storage solutions, in some cases over 40,000 node scale of GKE clusters, while maintaining data availability and performance. This has been battle tested by some of our largest customers. However, usability was a challenge at this scale, which we have solved as we have aimed to make storage boring and easy to configure, oftentimes transparently, simply based on your workload itself. We've launched storage profiles to automatically configure and optimize GCS. Lastly, inference at scale requires custom storage solutions and to maximize the metrics that matter the most, such as tokens per second throughput and decreasing time to first token latencies. We've introduced KV cache offloading and prefix-aware routing to further improve inference at scale. We've also solved problems related to model loading by integrating with Run AI Model Streamer. Since this is a small room, or not a small room, but a smaller crowd, I'd love to have this as interactive as possible, so please feel free to ask questions along the way. We'll also have a time for Q&A at the very end of the talk. It wasn't too long ago that stateful workloads on Kubernetes was still questioned as a viable strategy and best practice. We've overcome that chasm at this point and seen an increase in all data-centric workloads running on GKE. From a recent Data on Kubernetes survey of enterprises, we see DBs that are still the top running workload on Kubernetes today and analytics workloads that are coming in as a close second. We continue to look for ways to minimize total cost of ownership for these workloads and provide tunable performance for Hyperdisk and GCS. AI/ML is also on the rise and as expected in driving new, innovative features while customers are looking to minimize cost. GCS Fuse and Managed Lustre are great solutions for these workloads. Approximately 40% of streaming messaging and real-time processing workloads are also running on Kubernetes today, as well, helping to facilitate AI/ML data pipelines. And we see the same trends in our GKE-specific metrics also. To put this into perspective and share somewhat of a historical narrative, data and access patterns have been evolving as we move from traditional enterprise DBs, message queues, and web content management systems to AI training and inference workloads, and now to post-training with reinforcement learning, agentic AI, and KV caching. We have to build storage solutions for each of these stages of the data evolution to solve specific problems, because if we don't, we run the risk of not fully utilizing precious accelerator resources. We saw in data 1.0 generation or era the challenges related to availability and reliability and moving from stateless applications to stateful workloads on Kubernetes. We solved these problems by building highly available data plane and control plane products using stateful sets and regional PD hyperdisk HA solutions. Now in data 2.0 era, we saw massive storage needs for greater throughput and scale, which were orders of magnitude higher than previously needed for enterprise databases. As AI models scale, getting data from storage to the compute layer fast enough became a bottleneck. New storage capabilities provided greater performance directly at the storage layer, reducing total cost of ownership and keeping accelerators fully utilized. On the inference side, we need lower latencies for faster response to serving requests and input prompts and model loading. We also saw a large increase in LLM training for inference, and we solved these challenges with managed Lustre and GCS fused with Rapid with fully integrated CSI drivers for your GKE workloads. And now with data 3.0, we see even greater scale as context windows and input-output prompt lengths grow to tens and hundreds of thousands, approaching 1 million tokens, or with agentic sessions that are lasting for hours or even days. Post-training activities like reinforcement learning are becoming more prevalent to improve the accuracy of models based on agentic reward function loops and require high-speed weight transfers between the trainers and the samplers. We'll talk about each of these today. But first, let's take a brief look at solutions we have for enterprise and vector databases as well as analytics. We see two main patterns emerging, using hyperdisk with storage pools or customers using GCS for long-term persistent storage. Mission-critical databases require low-latency, high IOPS to keep users happy. They need continuous uptime with security and resilience. Hyperdisk provides performance, capacity, efficiency, and protection at exabyte scale. AI/ML customers also use hyperdisk boot disks for ephemeral storage, particularly on TPU-based VMs which don't have local SSDs attached. We are seeing an increasing need from customers to minimize their TCO, and for this, we recommend storage pools or exapools. Storage pools intelligently and efficiently manage your storage utilization as a shared resource across the GKE cluster. Pools are adjusted automatically as needs arise and as capacity grows or shrinks. AI workloads require massive scale throughput at consistency, low latency, often with highly correlated peaks. Storage pools, now exapools, provide the highest performance and highest capacity block storage per AI cluster of any hyperscaler out there. One of the challenges we see, though, with block storage is the massive number of different options and solutions across persistent disk and hyperdisk. GKE customers typically use custom compute classes to optimize and automatically identify the best node or VM type to run their workload based on what is available capacity-wise. But not all storage solutions work with Gen 2, Gen 3, and Gen 4 VMs. Depending on which node the pod is scheduled to run, it will need a dynamically selected block storage volume. That's why today we're announcing dynamic volumes as a single storage class that automatically chooses the best block storage option and works seamlessly with custom compute classes. You simply specify the performance that you want in terms of throughput and IOPS, and we take care of the rest. But workloads typically aren't static either and require varying levels of performance. Instead of recreating a disk or rescheduling pods, Customers need the ability to dynamically update the throughput in IOPS provision to right-size their workloads based on the demands during its life cycle. We now support dynamic updates through volume attributes classes, which allow you to adjust the performance of any disk on the fly without any downtime. We've heard from customers that dynamic volumes greatly simplify their block storage provisioning workflows on node pools using custom compute classes. They automatically choose between PD or hyperdisk, providing and provisioning the performance in terms of throughput and IOPS that are needed to meet their requirements based on the compute classes actually selected. Another pattern we typically see is with GCS for analytics and databases. Customers still choose hyperdisk for storing metadata and use local SSD as a caching layer, but their long-term storage on persistence layer is at GCS. Here to talk more about these types of solutions is Vinay from ClickHouse.
Hey everyone, my name is Vinay Suryadevara. I'm a senior software engineer at ClickHouse Cloud. I work in the cloud infrastructure team. So today I'm going to just talk about how we built ClickHouse Cloud on GCP and what kind of performance tricks we need to do to kind of reach performance and scalability requirements that are required for an enterprise database. So before we get into that, what is ClickHouse? ClickHouse is an open source OLAP database. It uses column-oriented storage for efficient performance. It has a wide variety of use cases, beginning with real-time analytics, but also warehousing, observability, etc. What makes ClickHouse special? How is it different from the other databases? ClickHouse is primarily built for speed. It's the fastest database for analytics. It's also cost-effective. It has a very impressive compression ratio, which leads to higher cost savings. It's highly scalable, and it also has a wide ecosystem of partner integrations. So coming to ClickHouse Cloud, right? What is ClickHouse Cloud? ClickHouse Cloud is a managed offering of ClickHouse open source in cloud. We have native separation of compute and storage. We use a proprietary shared merge tree table engine that allows us to scale both compute and storage separately, which is kind of required for any kind of cloud offering. Apart from object storage, which is what we use for a storage layer, we also use a variety of disks, especially local NVMe disks, to kind of reach the performance parity as compared to a shared nothing architecture. So ClickHouse Cloud is available on GCP. It's also available through the GCP marketplace. We already have thousands of ClickHouse services running in production on GCP right now. In terms of the compute and storage layer, for compute, we utilize GKE. All of our ClickHouse instances run on Kubernetes, so we utilize GKE. And we've actually received a lot of benefits from GKE, one of which is the optimized utilization feature, which GKE offers right out of the box. This means that we can do bin packing on our pods and ensure that we use the lesser number of nodes, and so that we have higher cost savings. For our storage layer, we use GCS, because GCS is a highly performant and scalable object storage. Apart from that, we also use a variety of other solutions, such as GKE persistent volumes for metadata storage, and we use NVMe disks for caching the hot data so that we can reach the performance parity. Recently, we've also been slowly migrating some of our customers to the Axion ARM instances that GCP has been getting, and we've noticed that we get about 40% faster queries, and also it's about 15% cheaper than the regular instances, which is a big benefit for us. So just to visualize how this would look, this looks like in ClickHouse, we have a VPC in GCP, and in there we have a Kubernetes cluster in which the customer workloads are deployed. So each customer workload is deployed in their own namespace. That's how we achieve the tenant isolation. And for each ClickHouse customer workload, underneath the hood, it consists of ClickHouse keepers and ClickHouse servers. ClickHouse keeper is our implementation of Zookeeper for coordination. And ClickHouse servers are our compute nodes, which actually run the queries. Each ClickHouse server, in turn, also talks to GCS for data storage. And also, each ClickHouse server has a local NVMe disk that is used for caching queries. Apart from this, we also use a wide range of GCP solutions, such as the cloud load balancing, cloud NAT gateway, cloud PubSub, etc. So GCP has a wide ecosystem of these solutions that we can use to build a managed solution on cloud. So now that we have an overview of like how the architecture looks, I'll talk about one particularly interesting problem that we faced and how we were able to solve that. So as I mentioned in the previous slide, we have ClickHouse servers running with local NVMe caches. What that means is if the pod restarts, then because these NVMe disks are attached to the node temporarily, if the pod restarts, that means it could wipe the local cache. And so when the next queries come into onto this pod, it means that we have to start populating the cache, and it will take a lot of time. And so we'll take a performance penalty hit because we need to go query object storage. Also, in ClickHouse Cloud, we have idling enabled, which means that if our customer service is not running any queries, we scale down the compute so that they're not charged for this compute when there's no queries running. And when this happens, this means that we lose the cache, and the next queries after the service wakes up are slower. The other problem is that since these caches are local to the pods, it means that if a single query runs on 2 different pods, that means that the data that is fetched from GCS is stored in 2 different NVMe caches, and that leads to data duplication. And finally, when we perform upgrades for our customers, we would like them to be non-disruptive. So we provision extra pods and make sure that they can serve up queries before removing the old pods. But what this means is that the new queries that come up do not have access to these caches, and so we have inefficient cache warming, and they're slower to begin with. So given this, we decided that we needed a better solution to reach performance parity with the shared nothing architecture. So if you see here, on the left is the current solution that we just talked about, where each ClickHouse server has its own NVMe disk. And ultimately, we do read and write through caching to GCS to make sure that the hot data always stays in the cache. So on the right is the new solution, which we call distributed cache. What this means is in a truly shared everything architecture, even the cache should be shared by instances. So that was the underlying principle here. And different customer instances now share the same distributed cache. Underneath the hood, what this distributed cache is another ClickHouse instance that is serving up this data. And ultimately, this data is, again, still persisted in GCS. In this new architecture, instead of doing when it needs the data from the cache, instead of getting it from the local NVMe cache, the customer instances will now talk to the distributed cache. That means that there could be a network penalty. So for this region, we deploy this distributed cache in each AZ where the customer queries exist. And then we also use consistent hashing to make sure that the same instance always reaches the same pod and data is not duplicated. Since the customer cache is now shared, we use MTLS plus hash-based partitioning to make sure that we ensure customer, the tenant isolation and data is not intermingled. So that's a high-level overview of how this new component called distributed cache that we designed, which is just ClickHouse server underneath that has pods that have local NVMe caches. But this is a shared cache between multiple instances. So this is the solution I just talked about. We have around 6 cache servers, 2 per AZ, multiple servers sharing 1 cache, consistent hashing. And we do the read and write through caching in this new solution as well to make sure that the hot data stays in the cache. Now, if we look at the previous issues that I just mentioned, when pods restart in the customer service instance, the distributed cache still does not have any restarts there. And so new pods that come up can access all the hot data in the cache immediately. And scale to 0 follows a similar pattern as well. And again, for the data duplication, we store the data once in distributed cache, and multiple server pods can now access this data. And finally, for rolling updates, it's the same story as well. So we were able to solve all of our performance concerns with the previous architecture that we had using this new distributed cache solution that we built on GCP. But this is just the architecture. The actual proof lies in the numbers. So if you look at how this distributed cache performs against the existing cache, so if we start as a baseline with the shared nothing self-managed architecture, where the data is stored on local SSDs and we don't have object storage. The obvious drawback there being that it's not a scalable solution. We'd need to do resharding every time we need to scale it. Then the second one is the ClickHouse Cloud with file system cache, which is what I talked about initially with local NVMEs. We see that on any cold queries, since we need to fetch the data from the object storage, we have a performance penalty on cold queries, but subsequent hot queries, again, reach the same performance as the shared nothing architecture because it's local NVMe caches there. With the distributed cache, The first time that we need to fetch this data from object storage, we will still run into the same issue of the cold query being a bit slower and the subsequent hot queries being faster. But the next time a different pod or a different node tries to query this data, now we don't need to go to the object storage, and we have this benefit of reaching almost performance parity with the shared nothing architecture on all subsequent cold queries. Like if a new pod comes up and it needs to read this data, it doesn't need to go to GCS, so we reap the benefits of distributed cache there. So this is how we built this component to ensure that, as an enterprise DB, we need to be highly scalable, but we also need to be performant. So this is how we reach both of those goals using the various storage tiers provided in GCP. Thank you. With that, I'll hand it back to Jason.
That's a great set of results that you got by building these storage solutions on top of GKE and GCP. But storage is no longer just a place to keep data. When training AI models, storage is the engine that feeds data-hungry accelerators. During AI inference, it's the access layer that makes its responsive acting as the source of context that AI agents need to be effective. When storage performance falls short, accelerators sit idle, and agents respond slowly, and data remains invisible to AI models. Storage bottlenecks can stall AI jobs and waste expensive compute cycles. Every time a training cluster waits on a read or a checkpoint write stalls, you're paying for accelerators that aren't doing useful work. In terms of model loading, similar patterns exist for inference, as we need to quickly load models to return inference responses to serving requests. From the beginning, connecting TPUs or GPU accelerators to disk at boot time is required to start streaming container image layers to what we call a secondary boot disk to decrease workload startup time. We also use hyperdisks connected to server-side VMs for hosting our managed Lustre offerings and instances. Lastly, we use model streaming through RunAI to directly stream that data from GCS to GPU, TPU high bandwidth memory. These storage challenges aren't getting any easier as models continue to increase in size from 15 terabytes of training data to 65 terabytes for Qwen. Checkpoints growing from 405 gigabytes to 7,500 gigabytes for DeepSeek v3, and model size scaling from 7 gigabytes to 1,250 gigabytes. This table shows a breakdown of some of the most popular models in terms of the number of training tokens, training dataset size, checkpoint size, model size, and throughput requirements to serve the state-of-the-art class models. So what is needed from storage for AI? Storage must provide high parallel throughput, low latency, and usability at scale to fully utilize accelerators. The realization is that storage can no longer be an afterthought. When designing AI/ML pipelines, data bottlenecks can become and have become a huge impact on GPU, TPU utilization. From data preparation to pre-training to model training with checkpoints and validation to inference with KV caching and post-training with reinforcement loops, data can be an iceberg in terms of quantity and scale. We enhanced Google Cloud Storage, recently releasing rapid cache and rapid buckets to meet these demands, all with full integration with GKE through CSI drivers. We also partnered with DDN to launch Google Managed Lustre last year, and now we have reached up to 10 terabytes per second of throughput. These two solutions can be used from a number of different stages in the pipeline that I described. Pre-processing petabytes to exabytes worth of data to ensure quality and format is ready for training, what we call pre-training. Then running training workloads on gigabytes to terabytes of input tokens with the output being the model parameters themselves. Scaling laws actually dictate that 20 times more tokens are needed for each new model parameter added. So you can see the explosion of data that's required. And then serving inference requests on models usually sized on the megabytes to gigabyte stage, updating model weights based on reward functions from sampling. And for each of these, we actually recommend cloud storage with Fuse drivers or Google Managed Lustre, which is our parallel file system offering. Diving a little bit deeper into Lustre, Lustre Parallel File System is an industry leading for organizations whose AI training and inference workloads require high throughput and sub-millisecond latency. Google Cloud Managed Lustre brings that capability as a fully managed service to our customers, and it's the most performant Lustre offering available in any cloud. As I said before, now delivering up to 10 terabytes per second of throughput, a 10x increase since last year. We have delivered a dynamic solution that is ready to scale for your training workload needs. The new dynamic tier delivers low latency performance required for intense AI workloads like training and checkpointing. We actually have measured the amount of GPU utilization with Managed Lustre compared to other storage offerings and found that it boosts that utilization by up to 54%. So this is additional utilization that your accelerators would ordinarily not have and wasted money if it was not being applied. This means cost savings with more fully utilized GPUs, not waiting for data. We also see this in terms of AI training jobs being 10 times faster, changing from an order of minutes to an order of seconds with Managed Lustre. We're also introducing GCS Rapid. Cloud Storage Rapid is a fundamental shift in AI infrastructure, bringing the power of Colossus, which is our high-speed data layer that Google Cloud runs on, to customers through a specialized AI storage subsystem. You're able to leverage industry-leading durability, massively distributed scale, and ultra-low latency with frequent IOs for the most performant workloads available using JAX or PyTorch or any other ML orchestration framework. Cloud Storage Rapid is now optimized out of the box for the most popular AI frameworks, as I mentioned. It comes in two variants, GCS Rapid Cache and GCS Rapid Bucket. It was actually GCS Rapid Cache was renamed, formerly Anywhere Cache, but it now is generally available and provides up to 15 terabytes per second of throughput or bandwidth with 20 million requests per second and sub-millisecond latencies. Rapid Cache, formerly Anywhere Cache, accelerates bandwidth for bursty workloads like model loading for inference, delivering an aggregate read throughput of 2.5 terabytes per second. With no code changes, this is an automatically easy no-brainer for customers to use and has ingest on write features, providing up to 2.2 times faster checkpoint restore times. However, with a plethora of mount options, different configuration for different workloads, and best practice guides that can often require a PhD in storage, we in GKE have made these solutions even more usable and user-friendly at scale by introducing something we call storage profiles. We build GCS Fuse storage profiles to solve these challenges and problems to optimally configure storage access based on the workload that you're running, whether that is for serving or for training or for checkpointing. Now, this is an example of a very poorly configured GCS Fuse, but one that happened to be just an out-of-the-box configuration. With storage profiles, we were able to see 170x performance improvement by correctly configuring and optimizing the GCS Fuse layer. What ordinarily or would have taken, this is extrapolated data time of about 39 hours to load Qwen 3. This was because the user, and this was a real-world customer scenario actually, they had disabled using file cache. They had multiple small files, which effectively resulted in a lot of random reads, and it created a lot of excessive shards, which were downloaded individually. So again, a real customer's configuration that was then utilized with storage profiles to decrease that model loading time to around 14 minutes. Given a demo of this real quick, just to show storage profiles, what we'll have here is an untuned, a tuned, and an optimized version of the profiles itself.
Today we will use the Cloud Storage Fuse CSI driver to deploy a serving workload using the Gamma 4 model, first with untuned configs, then with manual tuning, and finally with the profiles feature to automate the tuning. Let's start with the untuned deployment. The deployment has a volume for the Gamma 4 model weights. And another volume for the XLA cache. The deployment has an inference server for TPU and uses both volumes. The model weights will take 6 hours to load. Let's manually tune the cloud storage fuse configs to improve this. We'll apply the same specs as before, but this time we manually tuned mount options and CSI configs for serving workloads for both volumes. We'll also configure rapid storage cache in our node pool zones. The caches are pre-created for this demo, so we'll skip creating them. We have improved loading waits to only 3 minutes. Now let's see how we can use profiles to automate this setup. The training, inference, and checkpointing profiles are pre-installed in our cluster. We'll use the serving profile. The profile is a storage class preset with recommended mount options and CSI configs for serving. To use the feature, the PV and PVCs must point to the profile storage class. That's just a one-line change. The feature scans the PV to check bucket characteristics to inform the recommendation. The PV annotations show that the model directory has 10 objects and 51 gigabytes of total data. Rapid cache has also been configured by the feature. We have improved model loading time to 3 minutes, again with no manual steps. This deployment is now ready to serve and use Cloud Storage Bucket with automatically tuned best practices for optimal performance using AI/ML workloads. Thanks for watching.
So in this demo, we showed how we went from a manually unconfigured, unoptimized GCS fuse to load model weights for Gemma 4 on TPUs, to a tuned version of this with many configuration options, many mount options and attributes, to finally using GCS storage profiles to be able to automatically configure and optimize the workload with a one-line change. The other solution that we have developed for this is called Run AI Model Streamer. Partnering with NVIDIA, we have simple commands to accelerate model loading from GCS when using VLLM or SGLang directly. This is fully integrated with GCS authorization and authentication. Last year, we announced a preliminary version of this, but now have customers like Vertex AI using this in production. And we compared model loading performance with a popular model repository and saw that it took around 164 seconds to load Llama 3 70B and only achieved about 0.8 gigabytes per second of throughput. However, using Run AI Model Streamer to load the same model with distributed streaming enabled, we were able to load this in only 15 seconds and achieve an 8.8 gigabytes per second download speed. This is the fastest way to load models into GPU or TPU memory and the simplest. This does not use our CSI driver interface, but integrates directly at the application layer with VLLM and SGLang and supports both GPUs and TPUs. Vertex AI has been using the GKE provided Run AI Model Streamer on GCS for Llama models, which when bundled with their own optimizations has helped them achieve 50% improvement in end-to-end model load time. With that, I'll turn it over to Mustafa to talk about AI infrastructure performance, which is no longer limited by compute, it's limited by the data plane.
Thank you, Jason. This is Mustafa. I'm working as a machine learning infra engineer at Character.AI. Character.AI is an interactive entertainment platform, over 20 million users. Our users spend up to 90 minutes in a day. We have a couple of business priorities and challenges. One priority is provide high throughput access to our massive training data sets without duplicating data across clusters. It comes with some challenges. One is large training jobs require petabyte scale data sets, parallel access from thousands of workers, fast checkpoint storage and recovery. Our approach with GCS Fuse is simple. Mount data sets directly from GCS to our deployment YAMLs with using CSI driver, and then keep single source of truth as data. The second priority is ensure inference service can load models, access data quickly while scaling dynamically. We heavily use auto-scaling, so it's necessary for us. The challenges here, fast startup times, reliable access to models. We started downloading models, but it ended up with somewhere network issue, and then we switched over and over. Slow storage access caused deployment latency and slower application startup. With GCS Fuse, we are using caching and local storage, provide consistent access to model artifacts, no more internet issue, reduce startup time, simplify model distributed across clusters. We have two use cases. One is training, serving large-scale training data sets to our distributed jobs. The second one is the model artifact distribution. We are training models and then serving them, and then back and forth. We have to serve, we have to run both at the same time. So we are using GCS Fuse under the hood. This is high-level overview. We are using GKE cluster, multiple clusters actually. We have training and then inference node pools. As you see here, we are using GCS and then local SSD cache. This architecture allows us to large distributed training jobs to scale without storage bottlenecks and enables high throughput data access without operational overhead. What we learned here, the biggest takeaway is that object storage works extremely well for AI. As long as your data plane is designed for high parallel throughput. GCS Fuse best combination with local SSD. Why? Training jobs repeatedly read the same data sets. Local cache dramatically reduces repeated object storage reads. Use as much as more node local SSD cache layer to achieve near disk performance. AI training workloads generate massive parallel reads. Without tuning, Fuse can become a bottleneck. Too many small files can hurt your performance. Structure your data sets for sequential or shard-based access like Parquet. And the other thing is separate training data and checkpoints. Training data and checkpoints have very different access patterns. The training data sets heavily read the workloads, checkpoints, large periodic writes. Mixing them can cause performance issues. We are using separate buckets for data sets, checkpoints, and model artifacts. Before handing over to Jason, I want to mention about our latest experiment. Lately, we have tested VLM's Run AI Model Streamer using GCS bucket. As you can see here, we tested a couple options. We started from downloading Hugging Face. This is our baseline. This is a very small model. It took 3 minutes. And then we tested, via model streamer. We see 60.2 improvements in here. Thanks, everyone.
Lastly, I want to talk about Data 3.0. This is the future, specifically in terms of KV caching and offloading. Long context lengths, as I mentioned before, are increasing in size to tens to hundreds of thousands to millions of tokens, and they either need to be cached or regenerated. We want to lower the time to first token and improve the tokens per second throughput by making these data operations highly available and accessible. And we found that large KV caches shared between accelerators with large capacity can result in 50% TCO savings and 60% less GPU hours from an otherwise what would have to be recomputed. For Llama 3 70B inference on a 6-node A3 mega examples, these gains are substantial with a 95% cache hit ratio. What this means essentially with KV caching is what you get is when common input prompts or system prompts are requested for inference, they typically have a similar output. And so we can cache those outputs rather than having to recompute them every single time and save on GPU or TPU accelerator utilization. We've been working closely with partners like LM Cache, and since full KV context lengths no longer can fit in HBM memory, we have to offload those into second layer storage tiers or RAM disks. GPU benchmarks show tiered storage with RAM, local SSD, and GCS or Lustre can improve time to first token and tokens per second throughput substantially. Offloading to CPU RAM alone gave us 44% time to first token reduction, and offloading it again to local SSD gave us a 69% throughput improvement for large prompt lengths. So key takeaways, again, as I mentioned before, GKE is the best place to run your stateful AI and enterprise workloads using our high-performing, scalable, and reliable storage solutions. Scale continues to increase with models and training data sets and tokens on the rise, and we need usable performance at scale to be able to take advantage of these benefits and fully utilize expensive GPU and TPU accelerators. And lastly, inference at scale requires specific storage solutions like KV cache offloading and storage tiering to maximize tokens per second throughput and decrease time to first token. Really appreciate your time today, and I would appreciate your feedback and any lessons learned. We'll be up here at the front, myself, Vinay, and Mustafa, if you have any questions. But thank you very much, and that is all.